Sorry, got it.
And now,
No,
now you have to choose again Zoom, like
Okay.
this. Sorry, you have to, because if you don't,
Okay. Okay, good morning, everybody. Thank you for being here. It's a real pleasure for me to introduce you Professor Keigo Fukumura, that is going to stay here for the entire week. So if something happens, okay, I continue. I will be slow. So, you will be staying here for the entire week, so please feel free to contact me if you want to have some chats with Diego in the next days. He will be hosted in the CNR building of the OS here.
You're still online. Zoom is working.
So,
Okay.
Professor
You just
Fukumura
did a
took his PhD at
Just the
the
sharing.
Otago State University in 2005, and then he had a postdoc working place there. Then he moved to the NASA's Goddard Space Flight Center and in Maryland. Then at a postdoc position at the Maryland University. Then he moved to the James Madison, Virginia in 2012 as a faculty member, and he was a Kavli Institute for Theoretical Physics Scholar at Santa Barbara during the 2015-2017 period. And currently he is a member of the XRISM guest scientist, and among other commitments for future missions such as New Athena, not New Athena, in the future. So he will talk us about the signature from the Accretion-Disk winds using future missions starting from XRISM. Thank you very much.
Okay. Thank you, Mauro. Thank you everyone for being here. I'm really excited to be in Bologna for the first time, and so far I've been really enjoying the hospitality and everything. And so I don't know exactly what your background is, so I'm just going to touch base on the basics of what we know about the X-ray accretion-disk winds, which we can study from X-ray spectroscopy, both from CCD detectors and also the dispersive gratings instruments. And what I'm going to tell you today is really interesting, but it's a very ambitious attempt, because soon we will obtain the microcalorimeter data, not technically for the first time, but pretty much for the first time for the X-ray community. And so to be prepared for what's coming, or for what we're going to see from microcalorimeter data from AGN and also the black hole X-ray binary systems, we have some ideas, and hopefully I can share a little bit of what we are trying to do in my collaborations. You will see how exciting that is. Besides PowerPoint, sorry, it keeps crashing. Maybe it's my computer. Okay. I don't know if it has to do with the presentation mode or not. Okay. Okay, so I just want to acknowledge briefly my collaborators, including some people here in this room, and my basic question that I would like to address is the following. So can X-ray observations ever identify how these powerful X-ray winds are driven and launched from accretion disks around black hole systems? And I think we can think of two things. One is the spectroscopic signatures that we can obtain from a state-of-the-art, really detailed spectral information, such as microcalorimeters on board XRISM Resolve, and then I believe in the New Athena XIFU. And also we can take advantage of some reverberation mapping if we have a high quality, high signal to noise data from a very short exposures. So this requires a very large collecting area, such as New Athena. But if you have a time resolved high quality X-ray data, then we can do a lot better the reverberation mapping, and that can also tell us something about how these powerful accretion disk winds are launched and accelerated. So for the next 20 minutes or so, I'm going to be focused on the microcalorimeter spectroscopic analysis. And this is just to give you the general context of where we sit in terms of Athena and also the upcoming XRISM data. So now we can really explore this new discovery space at the high energy resolution parameter space, even from relatively dim sources. And I'm going to emphasize on these two populations of outflows. One is the warm absorbers, which have been historically known for many decades, since 80s, and then more recent discoveries of ultra-fast outflows. Okay, so I was very happy to see the XRISM being successfully launched in September, and I think we start getting the very first microcalorimeter data early next year during this performance verification phase. Okay, but for the time being, let me just give you the brief introduction of X-ray winds, both warm absorber and UFOs. So that parameter space in terms of quantum density as a function of velocity, illustrates the difference between different populations of outflows. And I'm going to be focused on X-ray warm absorbers, which has the modest quantum density and sort of slow to modest velocity properties in comparison with the ultra-fast outflows, which is much highly ionized, and it carries more quantum density. But I just want to point out that these outflows are ubiquitous across different populations of AGN. It's not just near Eddington or super Eddington, very bright AGN. We see these UFOs in sort of canonical, typical radio quiet, Seyfert 1 AGN. Not to mention some exotic extreme environments like ultra-luminous X-ray sources or lensed quasars, and even from tidal disruption events, we see relativistic outflows. Okay. It's not just AGN. When you look at the nearby galactic black hole X-ray binary sources, we see powerful winds from many transient sources. And so I think that's something we can learn from them to apply to AGN outflow physics. And I'm not going to talk about the non-canonical UFOs, which is sort of not really the typical UFOs, highly ionized, high quantum density, high velocity, ultra-fast outflows. There are some untypical UFOs. And that is not really easy to model, but so I'm going to exclude those populations. Okay, so just as an example, this is one of the sources that XRISM is planning to see as soon as PB phase starts. So it's a radio quiet, typical, canonical, stereotypical Seyfert 1 AGN 3783. And we are interested in this particular AGN because we have known multiple outflow components at the same time. So that's a very ideal, good case object to study outflows in general. So multi-ion warm absorbers, this has been historically known. And there's an indication from Tombesi sample that the 3783 also shows the ion K ultra-fast outflows, as you can see. So the blue shift is about 10% of the speed of light with a high quantum density. And if you look at the variability of the soft X-ray continuum, Seyfert AGN like 3783, among others, experience a very interesting continuum variability, as you can see in this flux changes. And so we do see these very heavy obscurers as well, in addition to the X-ray absorbing outflows. Okay, so just to give you the setup of different driving mechanisms, since we don't really know what kind of physical mechanisms are driving these outflows or obscurers, typically we can think of continuum radiation. So this is purely electron scattering. If you have a huge continuum X-ray, then the electron scattering itself can push the gas to a certain velocity. We expect that process to be very effective, from near Eddington or super Eddington sources, but the 37, 83, and typical Seyfert are not really going to that high end in luminosity range. If you don't have near Eddington or super Eddington continuum X-ray flux, you can still push the gas to some velocity if your UV component has a very strong flux. So this is a UV line driven disk winds. So there are some simulations that show that if the gas is not completely ionized, and if you have a huge UV emission, that can be a good source to push the ionized gas to certain velocity level. And so Takehashi Matsui is one of the pioneers to simulate the spectrum based on the UV line driven accretion disk winds. And then there are some characteristics about this kind of line driven outflows in terms of some radiation components. Okay, and you can also think of the thermal radiative driven. So if the accretion disk is really hot, then you don't really need the radiation, but you can just push the gas with the thermal pressure, thermal force. This does not seem to be very effective in AGN, but this is considered to be the candidate mechanism for black hole X-ray binary disk winds. But again, you need to have certain geometrical setting for this thermal driven outflow to work. And so, and also you can't really get the gas to a high velocity range. So definitely UFOs are not likely to be driven by thermal radiation. It's probably radiation driven or something else. So what we are advocating is the magnetic wind, which is based on the Lorentz force given by the open global magnetic field threaded through the extended region of accretion disk. So this is one of the simulations that we did in the past. The accretion disk is assumed to be very thin, and then you assume that the magnetic fields are distributed over many decades in radius on the accretion disk. And the plasma on the disk will be accelerated and efficiently launched from toroidal motion to the poroidal motion across the affine point. So these are the simulated streamlines of the MHD-driven outflows, and you can see the background color distribution of density on the right, and then ionization parameter on the left. And just so you know, ionization parameter is basically the luminosity, the photon density divided by the gas density. So you can see the comparison between the radiative field and the particle field. So the MHD wind has the most dense region on the accretion disk because that's where the gas is distributed as a reservoir for the outflow. And so that's the magenta purple region on the right panel. And then as the gas is launched, being accelerated, it gets more tenuous, more and more tenuous. So it is the least density in the funnel region where the opening angle can be very small. And in that the funnel region where we don't see magnetically driven winds, maybe perhaps that's where we see the relativistic radio jets, which is driven by some additional mechanism like black hole spin. Okay, so that's the mathematical framework. We numerically solve ideal MHD coupled to the Grashof-Shafarov equation to determine the magnetic field structure and also the density distribution and ionization distribution. And then we need to do radiative transfer calculations to actually determine the column density. So we use typically we use X star for post-process calculations. I'm not going to talk about this too much today, but it's really helpful and important to consider not just one single very prominent absorption features, namely ion K absorption features like ion 25, ion 26, which is usually the most prominent absorption features in the spectrum. But we also see some low ionization absorption features in soft X-ray band. So it's important to see this kind of absorption measure distribution, how ionization features across different X-ray band are distributed. Okay, so this is the paper that we did last year. So we try to focus on the typical radio quiet Seyfert UFOs, not necessarily very extremely bright nearby quasar like a PDS 456. So we chose some particular parameter ranges that are more or less relevant for radio quiet Seyfert 1 AGN, such as inclination, photon index, and strength of optical counterparts relative to X-ray flux, which is alpha OX. And then we have some knobs to change the wind properties, like how this accretion-disk wind density distribution is varied, and also the density normalization of the wind, which is determined at the accretion-disk surface at the innermost launching radius. So we parameterize those quantities and then simulated the absorption features. So after we did the post-process radiative transfer calculations, you get something like this. So this is the column density for different charge states of different chemical elements, iron 26 down to oxygen 8, for example, as a function of ionization parameter in log space. And you can see that they are kind of sort of distributed in a narrow ionization range. At least the peak, they are sort of distributed in a narrow range, like a 4 and 5. And when you look at the velocity of these column densities, it is 10% of the speed of light. So right off the bat from this figure, we can see that it's going to imprint the blue shifted absorption features for different ions, not just ion K absorbers. So that's what we find out from the simulated spectrum, and we found that all these absorption features are symmetric, being extended to the blue tail, and we argue that this may be the telltale sign of magnetic wind. And so here is the sorry. Okay, I have a few more slides. Yes. Okay, I think I can get through. the end. Okay, so these are simulated absorption features based on MHD framework. It may not be obvious from this, but especially from ion K or maybe an oxygen line, you can see a little asymmetry. So it's not really a Gaussian looking at symmetric absorption feature. It's shifted, it's more skewed towards higher energy band. And that's because MHD-driven wind tends to produce more higher velocity quantum densities compared to the lower velocity quantum densities. So this really is reflected in the shape of the absorption features, not just ion K band, but throughout the X-ray band. And so so we looked at the parameter dependence of photon index dependence, alpha OX dependence, inclination dependence, and also this P is the density dependence. Now, when you scale down this velocity to a lower velocity, we still see this skewed asymmetry. And these are independent calculations done by the Chakraborty and the Petrucci group. And they also saw this skewed asymmetric blue shifted absorption features. And this is very hard to fit with just a single Gaussian because of the shape, because of the asymmetry. And so you can definitely tell that it is not the just a symmetric profile. And this illustration sort of schematically concludes what we are trying to say. So it's not the symmetric profile if we have this MHD driving gas property. And so the red one is the MHD driven. And if you think that the gas is asymptotically accelerated, as in the typical line driven scenario, you actually expect the opposite skewness, which is the cyan, the light blue. And so they're not really they don't agree with each other. So you can sort of discriminate one from the other. Not to mention that the Gaussian and the thermal driven winds, they are sort of symmetric and narrower. So our hope is that with the high quality signal to noise microcalorimeter spectroscopy, we might be able to distinguish one from the other. So that was our hope. Okay, so the more realistic, but we don't know what realistic really means at this point in terms of Athena instrumentations. But with 10 kilosecond Athena, sorry, so the simulations that I showed you in the previous slides are the XRISM simulations. For 10 kilosecond Athena, you can see that asymmetry, and then you can see the difference between MHD driving and the line driving. Again, the skewness is opposite. And that is originating from how gas is accelerated and how density changes. Okay, and here's another example for particularly for PDS 456, the courtesy of James Reeves and the Gabby here. And so you can see clearly the asymmetry and skewness. Okay, so I think I only have 2 slides or so. Okay, and another point that I want to make is that so I talked about the UFOs, ultra-fast outflows, in the context of a magnetic driving scenario. Now, of course, UFOs are not the only absorbers we see. We see lots of different warm absorbers in sort of in still situation. So in this simulation, we incorporate 3 different warm absorbers, different kinematics and different quantum densities. And we also have this relativistic refraction components along with our MHD UFO components. And so that is the top and middle simulated spectra. And I want you to pay attention to the bottom one, which is basically the composite total spectrum minus MHD UFO components. So the deficit that you see is accounted for by this MHD-driving MHD-driven outflow components. And so again, you can see from different chemical elements, the UFO components, and this is a 200 kilosecond XRISM result, and you can tell the asymmetry again. The ion K is also extended to a higher energy band, and so is oxygen A. We did the 10 kilosecond Athena, and it's, of course, it's even more enhanced, so that's very encouraging. And so so our hope is to resolve that very fine okay, third time charm. I think one or two more. Yeah, okay. Yes, I was here, and then two more slides, so I think I can I can go through that without crashing. Sorry about that. Yeah. So UFOs are, so those are the UFOs. And then the last components that I just want to quickly tell you is the AGN obscurers. So back to 3783, which is one of the PB targets in the XRISM result. We see these very heavy obscuration. So these, we don't really know what's obscuring these soft X-ray band. There are some ideas that maybe some different components of accretion-disk wind is sort of protecting or shielding the outer part of the accretion-disk. We see this long time lags and the short time lags depending on the obscuration magnitude. And so in this storm 2, HST campaign of Markarian 817, these authors postulate that there has to be some kind of inner obscurer which is blocking the X-ray illumination, such that that the UV absorbers respond differently depending on the innermost obscurer. Okay, so we have this idea in this MHD driving context. So maybe the inner part is permeated with a very strong magnetic field, and so maybe these winds are part of the obscurers, and they can shield the strong X-rays depending on the geometry of the wind, magnetic wind, and you can't really see the details, but you can see 4 different morphology of the MHD wind depending on the angular momentum and energy. So maybe the way MHD wind is obscuring, we see this kind of soft X-ray obscuration, and that's just a very preliminary calculations of obscuration of Asian spectrum, and it seems like it's doing the right thing from consistent with observations. So that's something we can also think of. And so the last slide takeaway, telltale asymmetric blue tail. So if it's really present, then we should be able to see, you know, even just a part of this spectral features from not from gratings, but maybe from microcalorimeter data. And it's always good to study multi-ion absorbers, not the strongest one. And I have also told you that the MHD UFOs are not really contaminated by warm absorbers. We should be able to separate UFOs because of this asymmetry, at least in the context of magnetic driving. And obscuration might be related to the innermost Compton thick outflow which may be driven by magnetic process. And so microcalorimeters are really, really important, and it's really indispensable. We definitely need the resolved data, and even more so from the future Athena. And so I'll stop here, and thank you very much for your attention.
Questions for the speaker?
Well,
Okay.
okay. Hey, thank you very much. So the difference in the line shape between line driving and MHD is mainly due to how the material is accelerated.
That's right. That's correct.
The magnetic driving, the acceleration is done in the very central region.
Yes. So because in the MHD context, the gas is connected to the magnetic field, and the magnetic field is anchored to the Keplerian Accretion-Disk. So it's the faster the inner the faster, because it's a rotating faster, and then as you go outside, it goes slower. But if you think that the gas is asymptotically accelerated, then it's the opposite kinematics. So yes, yeah, I think it's a kind of interesting idea if that's what it is.
A naive question, I mean, the asymmetries are very tempting and probably reveal a lot, but do you have a feeling of how many sources you'll be able to detect at this level, signal to noise, to actually distinguish? What kind of flux do you need?
Yeah, so what kind of flux? Well, definitely the brighter the better, but I think well, so just to give a number, 10, even 10 to the minus 11 is sufficient. And so it doesn't have to be super bright, like PDS 456, because particularly for ultra fast outflows, according to this model, this particular model, this asymmetric feature is relatively broad, and so as long as, even if you don't have extremely high signal to noise data, as long as the feature is broad enough, then we can tell if it's which way it is extended, or if it's.
But there is a list of and we got a list of targets that are ideal, and the hope is obviously in the kind of a local universe. Obviously, Athena then is going to allow us to even look, because the peak of this where we think that the peak is around Z or 2 or 3, that's when you get a peak of accretion, when it's really, and therefore we think that the most powerful outflow there are at that. But yeah, so hopefully with this we can understand, and then with Athena we could actually observe even a higher redshift. And but yeah, that's it.
How sensitive you are on the intensity of magnetic fields that you need?
Consider them.
And are the numbers you get to produce these winds consistent with what you would guess from maybe slightly different objects, but like M87, for which there are now very detailed estimates?
You mean the magnetic field strength?
Yes.
Yeah. So for
to the disk, even if M87 probably is a different disk, but
yeah, because yeah, I think it's sensitive to how optically thick, or how much mass you have in the disk. So M87, I think it's I don't remember the magnetic.
No,
Yeah, I don't know. Yeah, they must have constrained the field strength from EHD image. I don't remember, but it's from this model, it's on the order of 10 to the 1,000, 10 to the 4 Gausses or so. This is the innermost magnetic field strength. And that's kind of the ballpark number that you get if you assume equipartition between magnetic energy density and, for example, the kinetic energy of the ultra-fast outflows. But yes, I think there's a big uncertainty in estimating magnetic field strength, but it's on the order of 10 to the 3, 10 to the 4 passes.
Excuse me, there is some calculation from May of 2012 that they're trying to connect the accretion of the disk to the magnetic. There is a connection with the Blackboard pane.
Yes. Yes.
So I'm curious if you use that just to constrain your
Yeah. So our model is very similar to the Branford pane. It's actually an extended version of it. We use a Contopoulos Lovelace, which has a gas pressure in it, whereas Branford pane is a cold gas. Okay. Yes. Yeah. So yes. So we can calculate the ratio between the mass flux to the magnetic flux. And basically, if you have a huge magnetic field, or if you have a lower mass flux, then it's easier to derive winds. And so once we constrain the magnetic flux, then we can calculate the magnetic field strength. But the first number that we directly get out of this model is the flux ratio between the mass flux and magnetic flux. But that can tell us something like 10 to the 4, 10 to the 5 Gausses. Yeah.
Last question, maybe?
Yeah. Technically, what is, or better, what would be the added value of SciFu with respect to this whole case?
The ionization parameter.
XIFU
Oh,
Athena.
XIFU.
Athena. What would be the added value of the Athena instrument?
Oh, added value. Well, so it's definitely the correcting area, and because well, with the XRISM, yeah, I mean XRISM is really tiny area compared to Athena, I believe. So you can do the same. You can do the same science. Yeah, with much shorter exposure. In other words, you can do time resolved variability for the same long exposure using Athena. Yes. So
not just a matter of statistics, but also time resolution.
Yeah, and I think the energy resolution is also
It's a little bit better.
A little bit better.
You really don't need it because the efficiency is large. Okay. So the advantage of Athena is that the area will improve by a factor of 50 the number of sources, which you can in time, and at the same time you can improve the time dependent. Why?
Yeah.
For reason time dependent analysis, I don't know about the stellar mass black holes, and then UFOs, the winds are different. You want to be able to time at least for short time.
Yeah. So like you said, we know that these outflows are variable, and it comes and go, at least from the galactic black hole accretion-disk winds. And so if we have very high the efficient the data from short exposure, then we can do similar science that we are doing now to galactic black hole X-ray binaries. We can see the time resolved variability study very more easily with Athena.
Okay, there are no questions from the remote audience, so
I'm sorry about